This video illustrates how to implement a binary tree in Java. I'm going to create my own binary tree using the class BinaryNode, as you see in this code. And what I'm going to do is I'm going to show you multiple constructors for it. One for a leaf node, one for a non-leaf node or an internal node. Then I'll show you two different ToString methods for it, a height method, a size method, which calculates the height and size respectively. Then I'll show you four different traversals of the nodes in a binary tree: the Preorder Traversal, or the DFS, Postorder Traversal, Inorder Traversal, and BFS. BFS stands for breadth first search, and DFS stands for depth first search. So I'm going to show you both of these traversals. All of these are for binary trees. What is a binary tree? Well, it's a tree in which every node has either two children, one child, or no children. And every node of the binary tree, in all the examples that I show you in this code, will be represented by an object of this class. This class is called BinaryNode. As you can see, it is inside the class called BinaryNode. It is inside the method, is inside the file called binarynode.java, and the file is inside the package called util. And I have some tests in the other package driver. There's a main class in it, which I go over it after I introduces the node. So the BinaryNode class has three public instance fields. The first one is element with the type E. As you see, E is a generic type, and I can create a binary node of any type I want. If I want my node to store, let's say, integers, then I will do binary node of integers. If I want to create a binary node that stores strings, instead of E, I will write a string, just like array lists or linked lists that are defined in the util Java util package. As you may be familiar with, those classes will receive an extra type in angle brackets, and that specifies the type of objects that you're going to store in the array list or in a linked list or even in hash set, tree set. This is a very nice feature of Java that allows you to customize a class using a type. In this case, E would be the type of data that I'm going to store in the binary node. But before I go forward, please note that this is not going to be a binary search tree. This is going to be a generic binary tree. Binary search tree is a special binary tree which has some special properties, and it should be defined for comparable objects. Here, E doesn't need to be comparable. It can be any type, right? So the binary node has an element, which is basically the data of type E. It has two references to two other nodes: binary node left, binary node right. You can think of binary node as an extension of a linked list node. A linked list node, especially a single linked list node, has only one reference to the next node. We call it the next. But binary node has two references. One is the left, one is the right. So you can think of binary trees as like 2D linked lists. And as I said, every node in binary tree might have no children, one child, or two children. How is it possible when we have two variables left and right? Well, if you see a null value for left or right, that means the child represented by that variable is missing. So if you have a leaf where the node has no children, then both left and right are going to be null. If a node has only one child, let's say the left child, then the right child would be null. If the node has only one child and that's the right child, then the left child would be null. And if none of them are null, that means the node has 2 children. Let me give you an example. I'm going to show you a very simple binary tree. Look at this. Here I have a binary tree with 7 nodes. One node is the root, one is the root of the left subtree, one is the root of the right subtree. We have 4 children: leftmost leaf, mid left leaf, mid right leaf, and rightmost leaf. I can make this tree using the binary tree that BinaryNode class that I just showed you. All I need to do is to create 7 different nodes and set their elements to numbers 10, 5, 12, 4, 3, 11, and 13. And for each node, I have to set their left and right to the proper values. For example, the leaves, all of the 4 leaves will have their both left and right references equal to null. So there's no left and right children for the leaves. Therefore, we're going to set their left and right instance fields equal to null. For the right subtree and left subtree, the left and right children would be basically all the leaves. For the left subtree, the left would be this, the right would be this. For the right subtree, the left would be this, the right would be this. And for the root, the left would be the left subtree, which has a value 5 in it, and the right would be the right subtree. Let's go back to the code and let me show you the 2 constructors I'm going to have for the binary node. First is going to be the constructor that I use for the leaves. It only gets an element and it's going to initialize the element, and the left and right children would be null. It basically calls the other constructor. The other constructor is the one that is used for internal nodes. Internal node is the opposite of leaf. Internal node is a node that has at least 1 child. Leaf is a node that had no children. And here what I do is basically I say, let's get all the 3 variables that are like 3 values for all the 3 instance fields that I have for this class. And let's initialize every single one of them. This dot left would be left, this dot right would be right, and this element would be element. So this is used basically for the non-leaf nodes or the internal nodes. Using these 2 constructors, I'm going to make the tree that I just showed you in the PDF file, which is this one. Let's do that. In the main, I will make those nodes and the whole binary tree. Let's begin by generating all the leaves. The leftmost leaf in the picture was 4, was a node with 4 value. Because 4 is an integer, I will create a binary node of integers, right? As you see. Then the mid left leaf would contain 3. I create another binary node. As you see, I use the constructor that gets only 1 parameter because these are leaves. So the left and right are both equal to null because they have no children. Mid left, mid right, and rightmost are the 2 other leaves. So I have listed all the leaves that I have from left to right. The values are 4, 3, 11, and 13. And then after I do that, I'm going to basically show you the next level. So these are the lowest level. We call this level 1, sorry, level 2. Then I'm going to make level 1, and then I'm going to make level 0. This is the nature of binary tree. When you make it in a bottom-up fashion. So the leaves are going to be the first nodes that are going to be constructed, then the upper level, level 1, and then level 0 would be the roots. So let's do that. After I make the 4 leaves, then I begin by making the left subtree, which is going to be a binary node that is made of an element 5, that's the data we store in it. It's made of 2 children, the leftmost leaf and the mid-left leaf. So I will take advantage of the nodes that I created before to construct my left subtree. The right subtree is made of 12 as the element, mid-right leaf and rightmost leaf as the 2 children. The left children is mid-right leaf and the right children is rightmost leaf. And finally, I make their root, which is made of element 10 and the as a value that it stores. The left subtree would be the left child and the right subtree would be the right child. The reason I called the children of root left subtree and right subtree is because you can think of each child of the root as the root of its own binary tree. So if someone asks you how many binary trees do you see in this picture, the answer should be 7. Why? Because you see a binary tree with the root equal to 10. That's one binary tree. The height is going to be 2. Tell you what height is. Height is the distance from roots to the deepest leaf. I see 2 more binary trees, one here, one here. The left one, the left subtree is a binary tree with the root equal to 5. The right subtree is a binary tree with the root 12. And then we have 4 more trees, each one with singleton nodes. This one is by itself a binary tree, which has 4 in it. This one is another binary tree. This one is another binary tree. This one is another binary tree. Each of these small binary trees have only one node, and that node is their root. That's it, right? So remember that the binary tree is defined in a recursive fashion. As I showed you in the video, we'll see lots of recursion when you use when you want to write algorithm for the binary trees, because of the nature of the binary tree that is defined recursively. And within a binary tree you have multiple binary trees. Not all of them, but most of the algorithms that we define for binary trees would be recursive, and they use recursive methods, right? All right, so let's go back to the code. We have other than these 2 constructors that I mentioned, we do have other methods. I'm going to begin with the ToString method. ToString is a method that we define in Java for classes to override the ToString method of the object class to represent the class. So because I said every node would be the root of its own subtree, I define the ToString method in the following way. I will basically take care of the base case first. The base case is if there is no left and right children, that means if it's a leaf, then you're going to only return the element followed by no string, or you can simply say element.toString. We don't know what the type of element is because it's a generic type, so we have to be careful. You can either say element.toString, or when you add the element with an empty string, the compiler is going to call the toString for element for you, so there's no difference. If it's not the base case, if the node is not the leaf, then you need to basically specify its left and right subtree. So we basically write down the element, and then in parentheses, we write down the left child, comma, the right child. So for the example that I showed you earlier, the ToString method should print basically the following. The root is 10, so it should print 10. Then in parentheses, it should print the left subtree. which is going to be 5 in parentheses 4 and 3, comma, then the right subtree, which is made of 12, 11, and 13. 12 is the root. In parentheses, I have 11 as the left child and 13 as the right child. Then I'm going to close this. I'll show you at the end of this video, like the ToString method output, it prints the same thing. And you may say, wait a minute, you just said all the operations are going to be recursive. Why didn't you define the ToString methods recursively? The answer is I did. It doesn't look like a recursive method because I have implicitly called the ToString methods, but if I want to make it explicit, I can say left that to a string. But believe me, you don't need to write this. When you add an object with a string, the compiler will automatically calls the ToString method for you. You don't need to mention it explicitly. So this is a recursive call. Then we do have a method for measuring the height or calculating the height of a given tree. The tree that I showed you had a height equal to 2. The height is defined as the length of the path from root to the deepest node, to the, or I should say, the maximum distance from root to any other node in the tree. So if you have a leaf only, if you have a binary tree that has no left and right subtrees, it's only a single node in a tree, and that node is the root, then the height would be 0 because by definition, there exists a single path from root to itself, and that's called a trivial path. And the length of that path would be 0 because it's made of no edges. In a given path, the length of the path is equal to the number of edges that are participating in that path. When you have only one node, the path from root to that same node would be of length 0. So the height is defined as 0 when you have only one node in a tree. That's why the base case returns 0. Again, this is a method in binary tree, so I will write it in a recursive fashion. If there is no left child, then the height of the whole tree would be the height of the right child plus 1. And I can explain it to you why. Imagine you have a node. Well, let's change the color. Black on black doesn't is not readable. So let's use the red color. So let's say you have a root and then there is no left child, but there is a right child. This is the right child. And this node is basically the root of its own subtree. Let's say the height of this is given as h, right? So you know the height of this node is, this subtree is h. So the height of the whole tree would be h plus 1. Why plus 1? Because you're going to go one level more. So the height of the actual tree would be the height of its right subtree plus 1, right? Same story if the, and then, you know, the right node was null. So there's no, I'm sorry, the left node was null. So there is no left child. The same story happens, or a similar story happens if there is no right child. You just need to measure the left child height and then add it by 1. And if both children exist for the root, then your job is a little bit more difficult because you have like both of them. Let's illustrate it in this shape. Let's say I have 2 children. The right child has a height equal to HR, and the left child has a height equal to H sub L, right? So How do you measure the height of the whole tree? You need to first find out which child is taller, because the taller child determines the height of the actual tree, because the definition of the tree height is basically the length of the longest path from a node, from the root to any node. So we care about the longest path. So we have to find out the maximum of the two children's heights. Basically, we need to use math.max, get the maximum of left child and right child's height. Whatever the maximum is, we're going to add it by 1, because again, the children are in the level 1, the root is on level 0. So whatever their height is, plus 1 would be the actual height of the whole tree. So that's basically the definition that we come up with, which is using recursion. And that's how you measure the height. Next, I'm going to show you another method. This method is measuring the size. Size means how many nodes we have. And it's pretty simple. It's just, again, uses recursion. You don't see the base case explicitly here, but you'll find out what I'm doing here as I go forward. First, I will count the root. Root is always, one node for the root, right? So size starts with 1. If there is a left subtree, so left wouldn't be null, then you add size by the left size. Of course, if there is no left child, you don't need to add size by the left dot size, because left doesn't exist. So there is no element or there's no node in it. So size shouldn't be incremented in that case. And then do the same thing for the right child. If the right child is not null, then find its size in a recursive fashion and then add it by the size. And at the end, you just return the size. That's it. That's going to count how many elements you have in total using recursion. So as you see, all the methods that I have shown to you are basically using recursion because of the recursive nature of the tree. Next, I'm going to do preorder. Preorder traversal of a tree is defined this way. We're going to traverse the nodes of this tree in a recursive, using preorder traversal in a recursive fashion. How does it work? How does preorder traversal works? Preorder means first traverse the root. So first, let's visit the root, which is 10. Then visit the whole left subtree in a preorder fashion, and then visit the whole right subtree in a preorder fashion. So I put placeholders L and R for the left and right subtree. Then we're going to go one level deeper and do the left and right subtree recursively. So let's traverse the nodes of the left subtree in a preorder fashion. Preorder means root, left, right. Root is 5, left is 4, and right is 3. Right? So I'm going to replace the L with 5, 4, 3. And then right. Right would be 12, 11, and 13. Right? So that's basically the final result. It's going to be 10, 5, 4, 3, 12, 11, and 13. That's called preorder traversal. How do you implement this in Java? It's quite simple. If you use recursion, you guessed that, still use recursion. Print the element first, then the element is going to be the root. Then you traverse the left subtree in a preorder fashion by calling the print preorder recursively. Then you're going to call the same function, the same method recursively now for the right subtree. But you're going to be careful if there is no left child. You don't need to print a preorder. You don't need to call the same method recursively for the left child, because calling a method on a null object will result in your program failure, and it results in a runtime error. So don't call a method for an object that is equal to null. Always double check. If it's not null, then you call. If it's null, then don't call it. Anyways, so that's the preorder traversal. Postorder is very similar. The only difference is instead of printing or visiting the root first, we're going to visit it last. So first you traverse the left child in a postorder fashion, the right child in a postorder fashion, and then you print the root. Inorder is kind of similar to the previous two. First you traverse the left child, then you traverse, or left subtree, I should say. Then you traverse or visit the root, and then you visit the right child. So it's kind of obvious by looking at their names. Because preorder has a prefix, it means that the root should be traversed first. Because postorder has a post prefix at the beginning, it means that you have to postpone the visit of root to the last step. So you need to first visit the left and right child, then you need to visit the root. And inorder, because it has the word in it, it means, the root has to be visited between the left and right child. So first left, then the root, and then the right child. But in all the three cases, we use recursion. I'll show you how this works at the end. Let's get into the two more very commonly used traversals of the binary tree. One is called BFS or breadth first search. Write it down. Breadth first search traversal. That's a super common traversals. It can help you solve many problems, including trees and graphs also, because there's a tree version, there's a graph version. We'll definitely get to the graph version later when we talk about graphs. But just to give you an idea how this works, this is probably one of the very few non-recursive algorithms, or I should say methods here, that we see for trees. It uses a queue. Queue is a first in, first out data structure. Queue is not a non-abstract class. You cannot instantiate from it. You have to use different implementation of a queue that is in the Java util package. I'm going to use the linked list version, and the linked list version is quite simple. Enqueue would be an add, and dequeue would be a remove. Here is how BFS works. First, you enqueue the root, which is this node, and then in a while loop, as long as the queue is not empty, you remove one element from the queue, or you dequeue one element, print it out or visit it, whatever you want. In this case, when we visit, we print, and then enqueue the children of that element that you just visited into the same queue. So we say, if it has a left child, add it to the queue. If it has the right child, add it to the queue. And that's it. This simple while loop will traverse the elements in a BFS fashion. What does BFS means? BFS means level by level from left to right. So first you visit the root, then the left child, then the right child, then the leftmost child, then the left mid child, then the right mid child, then the rightmost child. So let's go back to the same example I had, and I show you what BFS does. BFS says visit the root first, then visit the left subtree and then right subtree, then visit the leftmost leaf, mid left leaf, mid right leaf, and then the rightmost leaf. So the answer, the BFS traversal would be 10, 5, 12, 4, 3, 11, and 13. That's called BFS, breadth first search, right? It is super useful for lots of applications. I'll show you multiple examples in the future. Anyways, let's find out how a queue can manage this traversal. Let's have a queue and let's apply the same algorithm I told you on this certain example. I'm gonna first push the root. I shouldn't say push because this is a queue, it's not a stack. I should say enqueue. Let's enqueue the root, which is 10, right? This is the tail, this is the head, right? So from this end, I will enqueue, from the other end, I dequeue. And let's use a different color, let's say blue color, and then I'm gonna do the while loop that I just showed you in the code. I'm gonna remove the 10, I'm gonna print it out, and instead I have to enqueue its children. Who are the children of 10? It's gonna be 5 and 12. So I will enqueue 5 and 12 into this queue. The next iteration, as long as queue is not empty, you have to keep doing the while loop that I showed you. So this next time I have to remove 5, print 5, and enqueue its children. What are the children of 5? 4 and 3. So I will enqueue 4 and 3 into this queue, right? Next, I will remove 12 from the queue, next iteration, print that, and enqueue its children. What are the children of 12? 11 and 13. 11 and 13, right? And in the next 4 iterations, I only dequeue, I don't enqueue anything because we are traversing the leaves. The leaves have no children. So first I remove 4, print it. Then I remove 3, print it. Then I remove 11, print it. And then I remove 13 and print it. Right? That's basically my breadth first search traversal, which is not the same as pre-order, in-order, or post-order. It's a new thing. All right, so I'll show you later how this code can successfully do it for you. And finally, printing DFS fashion. DFS is the opposite of BFS. BFS means breadth first search. DFS means depth first search. When it comes to trees, depth first search is equivalent to pre-order traversal. You may say, well, if it's the same as pre-order traversal, why do you have like 2 different names? Why do you have DFS and pre-order? The reason is pre-order is only used for binary trees or generally like trees, not for graphs. But depth first search has a much more applications for not only trees, but any type of graph. It can be simple graph, it can be directed graph, it can be directed acyclic graph, directed graph with cycle. It is super, super useful for graph applications. And how does it work? Basically, if you replace Q in the algorithm of BFS by stack, replace remove by pop, replace add by push, and swap the left and right add. So first push right and then push left. Then you're going to get the DFS traversal. So replacing Q by a stack will make BFS into DFS, right? DFS would be basically preorder traversal. So if you replace the Q with the graph with the stack, then you will traverse this tree in a DFS fashion. Why do we call it DFS? Because it's depth first. You go all the way down 10, 5, 4, and then you go back, and then you traverse this. After this, you go to the next subtree, you traverse 12 and then 11. Then you get back and you traverse 13. So as you see, it traverses in a depth first search fashion. And a better example of difference between DFS and BFS is when you're solving a maze puzzle. Maze is basically a map with multiple barriers and walls, and then it has a start point and an end point. And then the solution is basically a path that reaches you from a start point to the end point, or a start to end, or source to target. The difficulty is there are too many walls. You have to make sure that you don't reach to a dead end. You have to traverse the whole maze to find out the answer. The answer to the maze can be either, can be obtained either using a BFS or a DFS. BFS patiently checks the surrounding of the source, and then in each round it increases its radius, and then it keeps scanning the whole map until it reaches to the target of the maze. But DFS is not like this. It goes one path, and when it reaches to dead end, it backtracks and it takes another route. And these are like two different approaches. In a lot of applications, BFS is better. In a lot of applications, DFS is better. And in some applications, both are equally good, right? But it's very important that you understand both of them. But as I said, this is just the binary tree concept. When we get to the graph concept, we're going to go much heavier on the applications of BFS and DFS. Anyways, so the last thing I wanted to mention is a cool ToString method for the binary node, which basically does not print the tree in a boring fashion using those parentheses that I did at the beginning of this video. Instead, it's just gonna draw this tree in the same way that you see it. So it basically draws it in three different lines. In the first line, it draws the roots. Then in the next line, it draws these two. And in the last line, it draws these two. How do I make that happen? I have to use a queue, and guess what? I have to do BFS. I don't want to explain this because it includes the in-queue of dummy node in it, and it gets really complicated. But what I want you to do is to look at it yourself. I'm going to post the code. You can look at the code yourself and try to make a sense out of it. It's nothing but using some tabs and new lines and dummy nodes to make the formatting beautiful. But the idea is basically to use a BFS. Let's finish this video by just going over an example of all of these methods that we have created. I'm just going to first print the tree that I created earlier. I showed you how to create it. So the same tree that I was explaining over it, I'm printing it first using the first ToString, which contains parentheses and all of those commas, and the format that I showed you, it uses nested parentheses. Then I will call the height and show you that it correctly calculates the height equal to 2. Then I show you the size. Then I show you the size should be 7, obviously. Then I show you the Preorder Traversal, then Postorder Traversal, then Inorder Traversal, then BFS, then DFS. And finally, I use the ToString 2, which uses BFS to make a nice string representation for the whole tree. So let's run it. And let's verify everything is correct. This is the first ToString method. 10 is the roots. The children are 5 and 12. Children of 5 are 4 and 3. Children of 12 are 11 and 13. Because 4 and 3 and 11 and 13 are leaves, they don't have children. So we're going to stop right here. What's the height? Height is 2. What's the size? Size is 7. I just want to show you how the size is calculated by just using a debug operation. Let's get into this line. And it's very important that you go to debug mode and try to make sure everything works properly when you have a recursive function. Recursive functions are not easy to understand in the first place. It's better to use the debug mode and go line by line into them and get the concept, because normally they are a little bit hard to understand. So let's step into the root.size. Says which one do you want to step into? I will say the size. And then let's go to the first line. Size is 1. Left is not equal to line. So we're going to get into the left tree, which is made of 5, 4, and 3, and find out the size. So I'm going to step into the size again. I'm now in the left subtree. The size is set to 1. Left is not null. We're going to get into the leftmost child, leftmost leaf, and find its size. Size should be definitely 1, but I'm going to step into it so I can prove it for you. The leftmost child is a leaf, so the leftmost leaf is a leaf, so it sets the size to 1, but both of its left and right children are null, so we don't call any method recursively in this call, and we simply return size 1. When I return size 1, I go back to the same line that I was for the size method of the left subtree. And I will add 1 to the size, which was already 1. So now size becomes 2. Then I will call the same method recursively for the right node of the left subtree, which contains number 3. It's a leaf, so I will quickly get out with size 1. And the size, which is currently 2, will be added by another 1. So their final value of size is 3. So now I'm going to get out of this, and I'm going to get back to the original size call, which was calling the size for the left subtree. The left subtree has 3 elements. So left.size returns 3. 3 plus 1 is 4. So now the size is 4. If you do the same thing, I just want to jump over this one because it gets boring, because it's going to be the symmetric situation in the right subtree. You're going to have, again, 3 nodes there. So I don't want to do this again. Size is going to be added by right.size, which is 3. So currently size is 4. 4 plus 3 is 7. So eventually you're going to return 7. Right? So that's how the size works. I did this just for you to see. You can you have the option of going to debug mode and go step by step into the recursive calls and figure out what's going to happen. If something goes wrong in your code that uses recursion, the best resource you have is IntelliJ. Don't try to come up with a shortcut and ask someone very early. Try to debug it yourself. That's going to help you understand recursion a lot better. Okay, so the rest, let me run it again. So the rest of it is kind of obvious. The Preorder Traversal is the same traversal that we were expecting. Same for the Postorder, Inorder, BFS, and DFS. As I told you, the DFS is identical to Preorder. But the reason we call it DFS is because DFS is used for general graph as well. And then finally, the cool ToString method that I showed you that uses BFS works properly. And, you know, look at this. This is basically the tree that I drew in that PDF, but it shows it in a text file. So there it is. And yeah, that's pretty much it. Thank you for watching and have a good day.